My name is Catherine Canatella, and this is my Black Hole Mass Lab 7. The objectives of this lab was to determine the mass of a black hole using Newton's second law of gravitational force of an object in regards to a star in orbital motion. The result was that the forces acting on the star were related to the changes in momentum with time of the star and the mass. Also, the mass of the black hole can be determined based on the initial information given. These are my initial conditions that were given in WebAssign. The star mass is 1.989 e to the 30th. The position of the black hole is negative 2e10, negative 5e10. And the delta t is equivalent to 1 day in seconds. And the last part of the code imports the position data. This is the code I used to find Fnet acting on the system. First, I found initial and final velocity, then initial and final momentum. I then found Fnet acting on the system using Newton's second law and the momentum principle. I'm now going to run my code. As you can see, the red arrow represents Fnet and always points toward the black hole. The black arrow represents F parallel. When the star is speeding up, it is in the same direction as momentum and velocity. When the star is slowing down, it's in the opposite direction like it is now. The blue arrow represents Fnet perpendicular. Fnet parallel demonstrates the magnitude of Fnet, while Fnet perpendicular represents the direction of Fnet. I then use the following line of code to print out the mass of the black hole. I use Newton's second law of gravitation, saying Fg is equal to g times n1 m2 divided by the magnitude of r squared. Fg is equal to Fnet. G is equal to 6.67 e to the negative 11. R mag was defined in the code, and m1 was equal to the star mass. Python then found the mass of the black hole to be 2.985 e to the 31st. What does it mean? Use the arrows provided in the program to visualize Fnet perpendicular, Fnet parallel, and Fnet. Discuss how these quantities are related to the delta p delta t parallel, and delta p delta t perpendicular. All these values were defined in my code, and I found the magnitude of each. The outputs are as follows. As you can see, each delta p delta t corresponds to its Fnet value and have exactly the same values. This means that the Fnet forces have the same values as the change in momentum over time. This corresponds well with the momentum principle that says Fnet equals delta p over delta t. Now I'm going to discuss how those values are different. Although it appears that Fnet and delta p delta t are exactly the same, they are not. They just have the same values. You can look at the following equation as a cause and effect statements in some essence. Because of a change in Fnet, momentum changes as a function of time. We cannot physically see the force acting on the object. However, we can see the rate of change of momentum, which signals to us that there is a force acting on the object. What if? Imagine the black hole whose mass you found was replaced by a different black hole, but still placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? If the motion of the star is the same and the black hole is at the same position as before, that means that the position and velocity of the star are the same. This leads us to the conclusion that the momentum on the star is also the same. Therefore, Fnet acting on the object must be the same as well. If the Fnet is the same, the only factors left in the gravitational equation are m1 and m2. Since all other values are the same, then for the value of m1 times n2 must also be the same. Therefore, if the star's mass is different, then the black hole's mass must also be different in order for the equation to still be satisfied.